Let us start our discussion of ethers with a story which happened around 2 centuries ago. The job of doctors during that time was difficult and very unpredictable. They didn't have good equipment or medicines as we have these days. An operation without anesthetic is difficult and painful to the patients. While conducting operations, the doctors used diethyl ether as an anesthetic mostly, as you can see here. Using ether as anesthetic was easy and it helped the patient to relax before the operation. One day, after anesthetizing a patient using ether, to sterilize the equipment, doctor put it in hot water. Unfortunately, this simple mistake caused inflammation followed by an immense explosion due to all the stored chemicals in the hospital. Later on, scientists found that ether has a very low boiling point and is highly inflammable as well as explosive in nature. This crucial knowledge about physical properties resulted in safer medical practices in later centuries. In this video, we will look into some of the physical and chemical properties of ether. Let us start the discussion with physical properties of ethers. As you can see here, the CO bonds in ethers are polar in nature. Hence, ether molecules have a net dipole moment. However, this weak polarity does not affect their boiling points. The boiling point of ethers are similar to that of alkanes with comparable molecular masses. For example, the boiling point of ethoxyethane and N-pentane are very similar. However, ethers have much lower boiling point than alcohols with the same molecular weight. As you can see in this table, the boiling point of 1-butanol is higher than that of ethoxyethane. This is because alcohol can participate in intermolecular hydrogen bonding while ethers or alkanes cannot. Molecules that can form hydrogen bond show higher boiling points when compared to those without hydrogen bonds in them. Now, shall we see the solubility properties of ethers? The miscibility of ethers in water resembles those of alcohols of the same molecular mass. Both ethoxyethane and 1-butanol are miscible to the almost same extent, that is 7.5 and 9 gram per 100 milliliter respectively. See, pentane is essentially immiscible with water. Do you know why? This is because alcohol can participate in intermolecular hydrogen bonding, as you can see here, while ethers or alkanes cannot. Molecules that can form hydrogen bond with water have a higher solubility in water. Moving on to the reactivity of ethers, you may find that ethers are the least reactive of all the functional groups. Hence, the cleavage of ethers requires drastic conditions. The acid-catalyzed cleavage of CO bond in ethers occurs in the presence of excess hydrogen halides or at a higher temperature. Here you can see, initially ether reacts with one molecule of hydrogen halide to give an alkyl halide and an alcohol. Further, this alcohol reacts with another molecule of hydrogen halide to give yet another molecule of alkyl halide and water. Among the different hydrogen halides, the most reactive is hydrogen iodide Hi followed by hydrogen bromide HBr and then hydrogen chloride which is HCl. Similarly, alkyl aryl ethers are also cleaved by alkyl halides, the aryl oxygen bond being more stable. The cleavage occurs at alkyl oxygen bond. This results in the formation of phenol and alkyl halide. Phenol and then alkyl halide. Next, we will see the electrophilic aromatic substitution reactions of aryl ethers. When you look into the resonance structure of aryl ethers, you can see that the electron density or negative charge is concentrated at ortho and para positions. As you can see here, this is the ortho position and this one is the para positions. This clearly indicates that the alkoxy group is ortho-para directing. Also, the presence of alkoxy group activates the aromatic ring towards electrophilic substitution reaction. Now, let us see a few examples of electrophilic aromatic substitution. In the bromination of an aromatic ether, say for example, anisole can be brominated with bromine in ethanoic acid. One thing to note is that unlike the bromination of benzene rings, this reaction does not require iron bromide catalyst. The activation of benzene ring by the methoxy group is enough to afford bromination. Next, we will see the Friedel-Crafts alkylation reaction. Here you can see the methylation of anisole. Anisole reacts with methyl chloride in the presence of anhydrous aluminum chloride to yield 4-methoxytoluene as the major product and 2-methoxytoluene as the minor product. Similarly, Friedel-Crafts acylation of aromatic ethers is also possible. Here you can see that acyl groups may be introduced at the ortho and para positions. Here either ortho positions or on the para positions. On anisole, using acid chloride in the presence of anhydrous aluminum chloride catalyst. Anisole reacts with ethanoyl chloride to yield 4-methoxyacetophenone as the major product and 2-methoxyacetophenone as the minor product. Finally, you can see the nitration of anisole using the nitrating mixture. As expected, nitration occurs at the ortho and para positions of anisole. Now, as we have come to the end of the video, tell me, how will you justify the formation of tertiary alkyl halide in this reaction? I can give you a hint. The first step of this reaction involves the protonation of ether, leading to the formation of tertiary butyl methyloxynium ion. Think about it.
Manorama Horizon. Learning made simple.